particular protocol, GTP version 2 C protocol. So we are going to study this protocol overall in a single shot, in the sense that once we cover this protocol, we will be covering almost all the interfaces that it involved in. So in one shot, we will be covering all the interfaces. So let's give a start. So the first concept that we have to learn in GTPC is about something called as tunnels. So what is these tunnels, and um, how do we create those? So we have this tunnel concept used for every GTP protocol. It is not applicable only for GTPC, but this tunnel concept is applicable for GTPU as well. So anytime when you toss this word called as a tunnel, it typically represents three important parameters on a node, which is used for segregating the traffic or separating the traffic. It could be signaling traffic, or it could be user data traffic. It could be any one of it. For example, if you are studying about GTPC tunnels are used for separating signaling traffic, and GTPU tunnels are going to be used for separating user data traffic. So, but the basic idea of the tunnels is always to separate different traffic. For example, these tunnels separate the different mobile user signaling messages, or these tunnels separate different EPS bearers data. So you might be creating multiple tunnels for multiple EPS bearers. So for each EPS bearer, we create a tunnel. So how we will be able to identify or separate a tunnel, basically? So what comprising inside this tunnel? A tunnel is identified with a combination of three elements called as a TEID and port number and IP address. So we have three elements. So if you combine these three things together, we call it as a tunnel. So always a tunnel gets created by any node for receiving the traffic on the tunnel, not for sending purpose. That means if you take that there are two GTP nodes are present, if node 1 created a tunnel by creating a tunnel ID, IP address, and the UDP port number, by using these three things, then the tunnel would be used by node 1 for receiving the traffic from node 2, not for sending the traffic. If node 1 would like to send the traffic on a tunnel, it needs the node 2 to create the tunnel, and then node 1 can use the tunnel to send the traffic. So any tunnel that is created is typically used for reception purpose. It is not used for the transmission purpose. So that is the primary idea. And what is the meaning of these three identities, and where do they work? TEID is at the application level, that is at the GTPU level. We will be using this TEID at GTP level. And below GTP, we have a protocol called as UDP, transport protocol. At UDP level, we will be having the port number, the UDP port number. And below the application, we have transport. Below the transport, we are going to have network layer. The network layer we have is IP layer. So the IP address at the IP layer level. So one parameter at one protocol layer. At GTP, it is a tunnel end identifier, TEID. And at UDP level, it is the port number. At IP level, it is the IP address. So if you create these three parameters and give the information to the other node by using these details, it can send some traffic to you. So you will be using this tunnel that is created for receiving the traffic. It could be any kind of traffic. It could be signaling messages, or it could be user data. Depending on whether we are learning GTP-C protocol or GTP-U protocol. It could be any one of the two things. So, um, so if node 1 created a TEID port number and IP address at application transport and network layer, node 1 can actually use it for receiving the traffic from node 2 once it creates the tunnel. So it is used for receiving the traffic. Or if node 2 created such a tunnel on his side with TEID port number and IP address, then by using the tunnel created on node 2, node 1 can send the traffic to node 2, or node 2 can receive the traffic from node 1. So it's always for reception. So that's very, very, very important aspect of GTP tunnels. So if you just remove these nodes and place our real components, for example, instead of node 1, you just use enode B, and node 2, we will use S gateway, for example. Now, if enode creates a tunnel, that tunnel would be used by S gateway to send the traffic to enode. Or if S gateway creates a tunnel on his side, that would be used by enode to send the traffic in the uplink direction to S gateway. So enode created tunnel would be used for downlink traffic sent by S gateway to enode, and S gateway created tunnel would be used by enode to send the traffic in the uplink direction to S gateway. So that's the vice versa roles. Of course, how do they exchange the tunnels is a different story. enode and S gateway, that doesn't have any kind of a control interface existing between each other, so they cannot exchange the tunnel IDs they have created with one another directly. They have to be exchanging the information through your MME component by making MME as a mediator. enode sends its tunnel details to MME, MME forwards it to S gateway, or S gateway sends its tunnel details to MME, MME forwards it to enode. So by keeping the MME as a mediator, we'll be exchanging the tunnel details from one another. But irrespective of how they are exchanging the tunnel IDs, but if the tunnel IDs are created, the only thing that you have to always remember is tunnel is used for reception. You just have to remember that concept. Tunnel is always going to be useful for receiving part, not for the transmitting part.
Sir, actually, I have a doubt here.
Yes,
Sir, if node 1 creates a tunnel, then it will receive the data from node 2. The
yes.
same channel can be used for node 2, right? To receive
No,
the
it
data
cannot.
from node 1. So why unnecessarily it will create two types of here tunnel for the two
It's a
nodes?
common sense point only. For example, if I tell you this, for example, if I create a tunnel, only you can send the data to me. If I create a tunnel, now you are asking me like how the reverse cannot be done, because that is conflicting the actual idea that I have told you already. That your tunnel is only for reception. Who created the tunnel? I have created the tunnel. You can send the data. I cannot send the data on the tunnel because I have created the tunnel. I cannot send it. I cannot send the data to my own unit. I have to send the data to you, to your machine. So you have to create the tunnel for me to be able to send the data to you. So obviously it is the opposite guy who need to create a tunnel to receive the data traffic, receive the traffic, right? So how can you use the tunnel? A simple rule. You can only receive the traffic on the tunnel. You created the tunnel. You can only receive traffic from the other side. You cannot send anything on it. It's used for reception. Okay. In another way of explaining it, if if your let us suppose Google server, um, Google server created some kind of a resource on its server, and they have told that by using this particular ID you can log in and you can transfer your files into my machine only for uploading. Let us suppose that it is upload server. You can only do the uploading. So you have got the details, you have logged in with the credentials or whatever, and you can start sending the files into that machine. You are not allowed to download anything from it because it is clearly told at the starting itself that you can only use this for uploading, not for downloading. Okay, so it is a one directional entity, as I have already told you. This is just one directional. You can only receive on that. You cannot send on it. As simple as that. Okay, so if you want to do both, so basically you are going to have this kind of an opposite thing. So you need to have a tunnel um, a tunnel created on the node 1, and you need to have a tunnel created on the node 2, so that these node 1 and node 2 can exchange the traffic on it. So the tunnel should be on either side. If you have the tunnel on only one side, you can only receive it. For example, let me quote another example here from our telecom sector section itself. We have the source in node B, we have the target in node B, and there is a handover taking place by X2 interface. Source in node B proposed the handover to the target. What does target do when it is accepting the handover? It is also going to send details to the source in node B about the tunnels that it is creating to receive the pending traffic. Now, who need to create the tunnel IDs here? Only target node we need to create the tunnel IDs, or source node we also need to create the tunnel IDs for X2 interface? Answer is only target node we need to create the tunnel IDs. What is the reason? Because target is not going to forward anything to the source. In fact, whatever the data that is pending on the source, only source can send it to the target. Okay, so pending traffic, either uplink pending traffic or downlink pending traffic, you wanted to send it to the target to for the further dispatch once the mobile goes into the target node B. So for this reason, who is creating the tunnels here? Only target guy is going to create the tunnel because he need to receive the data. So he creates the tunnel IDs, including the IP address and UDP port details. It will convey that information to the source. With the help of it, source will be able to send all the pending traffic for the bearers to your target node B. Target node B can receive it, and once the mobile arrives into his cell, target node B can start sending the data to the mobile. He can do that. So source node we never need to create the tunnels because he's not supposed to receive anything from the target. Now these tunnels are one directional tunnels here, only happening in one directional way, like from only source node B to target node B. At least if you take a normal node B to S gateway scenario, um, node B need to send the traffic in the uplink direction, so it requires S gateway's tunnel details. Yes, gateway need to send the traffic in the downlink direction to enode B. It requires enode B tunnel details. At least here it is bidirectional tunnel. We require one tunnel to be created on enode B, one tunnel mechanism to be created on S gateway. But here it is not bidirectional. It is unidirectional. So because there are unidirectional possible, a lot of unidirectional possibilities would be there in GTP mechanisms. That is why they have created the tunnels. Um, one-sided tunnels they have created it. So if you create a tunnel, you would only be using it for receiving. So if you are allowing anybody to send the traffic to you, you create a tunnel. That is the idea that goes here in GTP mechanism. It is applicable for both control plane as well as user plane. So how many tunnels we are going to require? Um, we need to identify that. So we would be identifying it. Let us suppose a case where UE is connected to a single PDN, single packet data network. How many tunnels that the mobile requires for his overall operations, and how many tunnels get created on different interfaces between different LTE nodes. We are going to recognize that. Okay. Now, this picture tells us the white line that you see is signaling, and the aqua color line that you see is the user data part. And you can also imagine the secondary thing. Um, you can also imagine the secondary thing that is related to that is related to your um, where we are talking about the tunneling concept. We already know from our protocol introduction where in which on which interfaces we are talking about the tunnels. So we use GTPC protocol between MME to S gateway. There we have to have tunnels. S gateway to P gateway we use GTPC and GTPU. So we require control plane tunnels as well as user plane tunnels. Enode B to S gateway we have the user plane. We have user plane tunnels here. So majorly we have the tunnels on these interfaces. MME to S gateway to P gateway, enode B to S gateway. Here we have the tunnel concepts. We don't need to discuss anything related to the tunnels on MME to eNode B interface or eNode B to UE interface because UE to eNode B, we have either SRBs, the white ones are called as SRBs, and the aqua color ones are called as DRBs. We won't call it or describe it as tunnels. And eNode B to MME, we will be using S1AP UEIDs to separate the traffic on the S1 interface, S1AP UEIDs. One UEID for recognizing the traffic of one mobile between eNode B to MME. We won't use the tunnel IDs. So we require tunnel IDs for segregating the signaling messages between MME to S gateway to P gateway, eNode B to S gateway to P gateway for user plane. This is control plane. These are user plane tunnels. So how many tunnels we are going to have when the mobile equipment is exactly connected to one PDN, exactly one and only one PDN? MME to S gateway, we have to create one pair of tunnel IDs. One tunnel ID to be created at MME, one tunnel ID to be created at S gateway to recognize that users signaling messages. There could be many users that are operational. So to recognize one user's um, information, we require this tunnel ID, one user's info. For example, MME and S gateway would be talking to each other about thousands of mobile phones. To recognize which mobile phone related data they are exchanging, they need to recognize that information with the help of the tunnel ID, GTPC tunnel ID. I mean to say GTPC TEID. Similarly, S gateway and P gateway also would be communicating about thousands of mobile phones related aspects. Even to recognize the users related, which users related control messages they are exchanging, they again need to create two GTPC tunnel IDs, one by S gateway, one by P gateway. This is for the control plane. Similarly, S gateway, P gateway need to exchange the data that belongs to the mobile user, like the data that belongs to the mobile related to the default EPS bearer, a radio bearer plus S1 bearer plus S5 S8 bearer. As part of the S5 S8 bearer, user plane bearer, we are creating two user plane tunnel IDs, one by P gateway, one by S gateway. S gateway will use P gateway tunnel ID for sending the uplink traffic. P gateway uses S gateway's tunnel ID to send the downlink traffic. Similarly, S gateway will be creating one tunnel ID for S1 user plane interface, and eNode B would be creating one tunnel ID for receiving the traffic from S gateway. S gateway creates the tunnel for receiving the traffic from eNode B. So totally how many tunnel IDs we have by assuming that mobile equipment is exactly having one EPS bearer right now, one EPS bearer mobile is having, which is a default EPS bearer. Um, so we require four tunnel IDs for user plane. We require four tunnel IDs for signaling for GTPC operation. So when the mobile is connected to a single PDN. Now let us enhance this situation. Let us assume mobile is still connected to a single PDN, but mobile equipment is having two EPS bearers. So there is additional EPS bearer getting created. EPS bearer in the sense a dedicated bearer. Already existing one is default. So when you see this additional EPS bearer getting created, one easy observation is that there is no additional tunnels we need to create with respect to signaling between S gateway to MME or S gateway to P gateway. We have only single white lines that are present. Each white line represents a pair of TEIDs between MME and S gateway to P gateway. So control plane, we don't need to create additional tunnels. We can recognize that user signaling messages with a single tunnel ID, whether the mobile is operating with a single EPS bearer or two EPS bearers. But when it comes to the user plane aqua color lines, we can easily see that there is the additional GTPu tunnels got created between eNode B to S gateway to P gateway. Additional aqua color lines we can see. So that represents that user plane tunnels have been doubled. Your control plane tunnels stayed as it is. Control plane tunnels did not change, but user plane tunnels have got doubled. Now, eNode B has got two tunnels, one tunnel for receiving default bearer traffic, one tunnel for receiving dedicated bearer traffic. Same way, S gateway is having tunnels, two tunnels for receiving uplink traffic. S gateway is having two tunnels for receiving downlink traffic from P gateway, and P gateway is having two tunnels for receiving uplink traffic from the S gateway. So totally, we have eight tunnel IDs created in between among these three units that are operating in ODB, gateway, and P gateway. Right now, mobile equipment is having two EPS bearers. So one default bearer and one dedicated bearer, two EPS bearers. Of course, uh, along with S1 tunnel, additional tunnels got created on S1 and S5, S8. We have the additional radio bearer also. There is a dedicated bearer also got created here additionally. Okay, so we take it for granted that mobile equipment is still connected to a single PDN. Further, to continue. And mobile equipment is going to get connected to another EPS bearer. So it is having one default bearer and two dedicated bearers. It is having. So again, there is no change with respect to the control plane. Your signaling, we have only single tunnels. Signaling. We have still single tunnels for between MME to S gateway to P gateway. So signaling tunnels have not been increased. But user plane tunnels, yes, one radio bearer got increased between E node B to UE. E node B to S gateway, one additional pair of tunnels have popped up for downlink and uplink operations. Say same similarly from S gateway to P gateway, also one additional pair of tunnels popped up. Of course, P gateway to PDN, the external bearers keep increasing every time. First time we have only one external bearer between P gateway to PDN, next to two, next to three. So with every EPS bearer increase, there is one additional external bearer as well. So totally we are operating with three user plane tunnels and one pair of control plane tunnels. So the basic idea that we get is control plane tunnels are recognizing which user signaling messages we are exchanging. It will recognize that part. Which one? Control plane signaling will recognize that. But whereas user plane, for every mobile you can have multiple tunnels to separate the traffic, to separate multiple EPS bearers that the mobile is having default and dedicated, because each bearer is going to have a different quality of service. Each application's traffic we might be sending on a different bearer to achieve different quality of service. That is why we are creating multiple radio bearers with different quality of service and different priorities, different bit rates, and multiple S1 tunnels, multiple S5, S8 tunnels. So we are creating everything multiple. But when it comes to signaling messages, there is no concept related to signaling that signaling messages must be sent with different quality of service or different priorities. Nothing like that. Yeah, for signaling quality of service and all that is not applicable. So only to separate out the every mobile's messages out of thousands and lakhs of mobiles that are operating, we need to create the corresponding number of tunnels between MME to S gateway to P gateway, the GTPc tunnel IDs we need to create. And please remember, here when we are learning it, we are not concentrating on learning either not GTPC or GTP. We are learning both actually. We are understanding GTPC mechanism as well as GTPU mechanism at the same time. In both the protocols, we have the tunnel concept. GTPC tunnels are segregating signaling message traffic. GTPU tunnels will segregate user plane traffic. That is the primary difference between them. All right. This is when the mobile equipment is connected to. Um, this is when the mobile equipment is connected to a single packet data network. It is connected to single PDN if the mobile is connected to. What if the mobile equipment is connected to multiple PDNs? multiple packet data networks. Is there anything that is going to get changed if the mobile gets connected to multiple PDMs? Let's observe that point. Okay, so UE is connected to two PDMs. Now, the moment the mobile equipment is connected to the second PDM, you can observe the differences. Of course, we can see that user plane tunnels have been increased. Between eNode B to S gateway, a fourth tunnel has come up. S gateway to P gateway also there is a fourth tunnel came up. And P gateway is linking one external bearer towards PDN2, second PDN. So user plane tunnels have been increased. But one other change that you see here is between S gateway to P gateway, we see that there is a control plane tunnel got increased. So earlier, as long as the mobile equipment is connected to a single PDN, the control plane tunnels are single only. Between MME to S gateway, we have single pair of tunnels. S gateway to P gateway, we have a single pair of tunnels created, irrespective of how many number of EPS bearers the mobile is having. As long as mobile is connected to one PDN. But the moment mobile connected to two PDNs, between S gateway to P gateway, one control plane tunnel additionally came up. So the fundamental rule they defined is the number of control plane tunnels the mobile is going to have will be proportional to the number of PDMs the mobile equipment get connected to. So if mobile gets connected to three packet data networks, S gateway to P gateway, we will have three tunnels. But that doesn't mean there will be a change between MME to S gateway. There is no change from MME to S gateway. It is a single tunnel, pair of tunnels we have created between MME to S gateway to recognize the mobile signaling messages. Only S gateway to P gateway, there is a change here. Why is that? The reason typically would be in order to connect to a two different PDNs, mobile equipment may take the services of multiple P gateways. It must be using a single S gateway and single MME always. Mobile must be using the services of a single eNode B, single MME, and single S gateway. It is a fundamental rule. But mobile can use the services of multiple P gateways. So here, mobile is using the services of two P gateways to connect it to two PDNs, two packet data networks. So to segregate that kind of a information, so S gateway to P gateway one, we have one signaling tunnel, three user plane tunnels for one default bearer, two dedicated bearers. S gateway to second P gateway, we have one signaling tunnel, one pair of signaling tunnels, and one user plane pair of tunnels for a default bearer towards the PDN2, packet data network 2. The fundamental rule in LTE is mobile equipment, whenever it gets connected to any packet data network, it must at least have one default bearer, minimum, bare minimum. If you are having multiple EPS bearers or not, that is a choice. But having a minimum one default bearer is very much needed, very much required. So that is that. Okay. So what is the overall rule strategy? If mobile equipment, irrespective of how many packet data networks mobile is connected to, irrespective of that fact, if mobile is totally having how many EPS bearers, that many number of GTPu tunnels will be there all across the network. eNode B to S gateway, total four tunnels, four pairs of tunnels we have. S gateway to P gateway, we have four in case a single P gateway is helping you to connect to two PDNs, or if two different P gateways are helping you to connect to two different PDNs, then we have the split. So three pairs of tunnels towards first P gateway and one pair of tunnel we have created between S gateway to P gateway 2. So the user plane tunnels have been split across the P gateways. But MME to S gateway, the number of GTPC tunnels are single, but S gateway to P gateway will be dependent on the number of PDMs the mobile equipment is connected, irrespective of whether mobile is using the services of single P gateway or multiple P gateways. That doesn't matter. So if mobile is connected to three PDN networks with the help of a single P gateway also, between S gateway to P gateway, we'll have to create three pairs of control plane tunnel IDs. When the mobile disconnects from one PDN, the corresponding control plane tunnel ID pair also will be removed. Now it will contain two pairs of tunnel IDs. If mobile disconnects from other PDN, another pair of tunnel IDs will be removed from S gateway to P gateway. Finally, mobile will be having only one pair of GTPC tunnel IDs between S gateway to P gateway. It is how that will work out. Okay, so that's the primary idea. So I hope you got this concept of how we are going to create the tunnels and segregate the traffic. Now, the user plane part, GTPU part is later, but if you look into the control plane rules, this is what that is described in the GTPC protocol document. So for control plane, each endpoint of a GTPC tunnel, we must have um, we must have um, one pair of tunnel ID, TEID Cs. C here stands for control plane on S5 S8 interface per PDN connection. Like depending on how many PDN connections mobile is having. If mobile gets connected to five PDNs, you will have five pairs of TEID Cs will be there. But on all other interfaces, wherever GTPC works, exactly only one pair of tunnel IDs must be working irrespective of the interface. So on what all other interfaces GTPC can operate, S3 interface, S10 interface, S16, S11 or S4. S3 is between MME to SGSN. S10 is between MME to MME. S16 is between SGSN to SGSN. S11 is between MME to S gateway. S4 is between S gateway to SGSN. On all these control plane nodes, we will be exactly having one pair of TEID Cs that need to be created per user for exchanging the signaling messages. But only specialty is on S5, S5 S8 interface between S gateway to P gateway. That will be dependent on the number of PDN connections the mobile is having. Mobile have five PDN connections. You need to have five pairs of tunnel IDs that need to be created. Okay. And if I go back to the previous slide, um, normally when they create the user plane tunnels, how they actually will exchange the information related to user plane tunnels. For example, if S gateway and P gateway created their user plane tunnels here, how do they talk to each other about the user plane tunnels? By using GTPC protocol. By using GTPC protocol messages, P gateway will explain S gateway what tunnel ID it has created. S gateway will explain P gateway what tunnel ID it has created by communicating with the GTPC protocol. So GTPC protocol is used for exchanging GTPU tunnel related information. Similarly, if eNode B and S gateway creates the tunnel IDs on S1 interface, eNode B tunnel ID information would be packed into S1 AP and sent to MME, and MME will forward that information to S gateway on GTPC protocol. Similarly, S gateway's GTPU tunnel ID details information would be packed into GTPC and it conveys to MME. Once MME receives it, MME packs it into a S1 AP protocol and send that information to eNode B. Because eNode B and S gateway doesn't have the control interface available with each other, the control protocol is not there between each other. Any information that they have to exchange between each other, they have to go through the mediator, which is MME here, which must be going through the MME. Um, but other than that, the user plane tunnel will be working directly between eNode B to S gateway. But before it starts working, they need to exchange the information. eNode B need to tell S gateway with the details about these tunnel details so that S gateway can pump the traffic to him in the downlink direction. Similarly, S gateway need to send his tunnel details to eNode B so that eNode B can send uplink traffic to S gateway. They cannot exchange this tunnel ID details directly as the control interface is not there, they have to go through MME. So that's the point. But irrespective of what interface we are studying, on all components, they will be exchanging GTPU tunnel related information by using signaling protocol messages. It doesn't matter which signaling protocols we use. On different protocol interfaces, we'll be using different signaling protocols. For example, S gateway to P gateway, we would be using GTPC protocol to exchange GTPU tunnel IDs. S gateway to MME, we will use again GTPC. MME to eNodeB, we will use S1AP protocol. So by using different protocols, you will exchange information related to GTPU tunnel IDs. But how do you exchange tunnel IDs that are created for GTPC? For example, if MME created a GTPC tunnel ID and it want to convey that information to S gateway, how it will convey? By using GTPC itself. That means GTPC protocol can be used for conveying information related to GTPC tunnels as well as GTPU tunnels, both. Even between S gateway to P gateway also, GTPC protocol is only used for exchanging information between S gateway to P gateway to talk to each other about what GTPC tunnels you have created, what GTPU tunnels you have created. You can send that information to the other guy by using GTPC protocol messages itself. So that means GTPC is self-serving. It'll help itself out. But whereas on the other hand, GTPC tunnel details must be exchanged by, GTPU tunnel details must be exchanged by GTPC. So GTPU here is dependent on the signaling protocols, whereas signaling protocol tunnel ID information can be exchanged between these two components by itself. You don't require anybody else to help you out there. Okay. So with that basic knowledge, we are going to get into the GTPC protocol. So we start studying the GTPC protocol and its logic.
Sir, one moment, sir. Could you please go back to the previous slide, sir?
Which one? The
Previous slide,
tunnels.
sir. Just previous slide. Yes.
This one?
No, not this one, sir. The figure one. This one, sir. Sir, actually, I a little bit doubt here. For a single P gateway, we need the number of tunnel ID depend on the number of PDNs. But
Uh,
multiple P gateway, I got that. I got the idea. But for single P gateway, it will depend on the number of PDNs. That part I have doubt, sir.
the simple reason is simple. They wanted to make it universal. They wanted to make sure that irrespective of whether you are using single P gateway service or multiple P gateway service, they wanted to follow a single rule. Dependent on the number of PDMs the mobile gets connected, they wanted to create that many number of GTPC tunnel IDs. It is ultimately it is a point of choice. They would have decided that if a mobile is getting connected to two PDMs with the help of a single P gateway, we would be using a single control plane tunnel itself between S gateway to P gateway. They would have decided it that way also. The choice was there for them because they can recognize by using a single tunnel ID only between S gateway to P gateway. They can segregate the user plane signaling messages. One tunnel ID, one pair of tunnel IDs are enough between S gateway to P gateway. There is no anything additional thing that is needed. But they have see any your standardizations are nothing but whatever is finalized is standardized. So it doesn't mean that it is the only possibility. They might have had the other possibility to have only a single tunnel ID, pair of tunnel IDs between S gateway to P gateway when we are using the services of one P gateway. It would have been, but they don't want to do that. They decided that irrespective of the fact that whether mobile is taking the service from one P gateway or two P gateways, we will always use multiple tunnel IDs even at the control plane level. So they decided it that way. Okay, so just a rule. It is not that um, it is not that that's the only possibility. You got it?
Yes, I got it, sir. Thank you, sir.
Okay. So format of the GTPC protocol messages. So every GTPC protocol message will contain two sections: GTPC header followed by zero or more information elements. We have the concept of information elements, which is already known to us, nothing but the parameters. So in every GTPC message, you will have a standard header followed by zero or more IEs, information elements. Uh, for different GTPC protocol messages, you will have different types of information elements present, but the header part is common. Header part is the common section, and information elements will be varying depending on which protocol message you are sending. For different functionalities, you will exchange different messages, and for different messages it will contain different information elements. It makes sense. For example, if you have to apply to government to get a passport, or to get a PAN card, details will not be similar. Details will be different to get a passport and to get a PAN card. So what the application forms will be different, and the parameters and the values you fill in the application forms will be different. Same way, for exchanging different types of information between the components, you require different information elements in different cases, depending on the functionality that you are talking about. So IEs can change, but header will be the fixed part. So what is present in this header? First, we'll look into the header section. So this is the standard GTPC header. Um, each line is 8 bits, which is 1 byte or 1 octet, 1 byte. So first parameter we have in the header is version, which is 3 bits. Because it is 3 bits, the possible values we can have is from 0 to 7, 2 power 0 to, sorry, 2 power 0 to 2 power 3 minus 1. 2 power 3 minus 1 is 7. So if you talk in terms of binary information, the values are starting from 000 to 111. So 000 is 0, 111 is 7. Binary information. So how many versions uh, that we can have in GTPC? Up to 7. But the version that we are studying is 2, GTP version 2. Because it is version 2, obviously the value is going to be 010. 010 represents a 2. This binary information represents a decimal value 2. So that represents GTPC version 2 protocol message. We have GTPC version 1 also. Version 3, version 4 are not yet defined. It will be for the future. Right now, only version 1 and version 2 are defined. Version 1 is used in your UMTS, and version 2 we are using it in LTE. So this is version 2, 010 is going to be the value of the version field. Okay. Next parameter, piggybacking flag. The next parameter is. So what is this piggybacking flag? Um, what's there in this piggybacking flag? GTPC uses a transport called as a UDP transport. UDP doesn't support message bundling like SCTP protocol supports the message bundling. GTP doesn't support the message bundling mechanism. So, if you want to transport multiple GTPC messages from MME to S gateway at the same time, we cannot do that by using SCTP. We cannot do that by using UDP transport. So they have decided, because UDP doesn't support it, they decided that we must be doing that at GTPC protocol level itself. That means the application protocol itself will be implementing the message bundling. So if MME want to send 5 or 6 small GTPC messages at the same time, we can club all those GTPC messages together into one single chunk message, and we can pack it into UDP and send it. Because UDP doesn't support the message bundling, they are implementing that message bundling mechanism at application level itself. For example, your UDP protocol doesn't support reliability. So who need to implement the reliability? reliability must be implemented by GTPC on his own. So we are going to study how GTPC implements the reliability also. But again, UDP doesn't support message bundling, so GTPC will implement message bundling on its own. How it will be done, we will study. But what this P parameter represents, if the piggybacking flag is set to 0, that means it is a single GTPC message. It is not bundled with any other GTPC message. But when the piggybacking flag is set to 1, you are explaining that this is not a single GTPC message. Indeed, we have combined multiple GTPC messages. That is what it represents. This P flag will represent whether it is a single GTPC message or it is multiple GTPC messages that are present here. So that is the point there. So that is the P part, piggy piggybacking flag we have. So then T stands for TAD flag. All 1-bit parameters always will be called as flags. So TAD flag, what this TAD flag represents? TAD represents a tunnel and identifier. So um, a tunnel and identifier is going to explain whether this TAD field that is over here, it is going to be present or not present. Normally, when the TAD will be present in GTPC messages, if MME and S gateway are exchanging any GTPC protocol messages containing TEAD, meaning is they are exchanging the GTPC messages with respect to mobile phones. That means they are UE specific messages. If they are exchanging the general GTPC messages, like the concept we have studied, like X2AP and S1AP protocols called as global messages, in that UEIDs won't be there in the global messages. Similarly, in case of GTPC protocol, you won't have the tunnel IDs present in case when we are exchanging global messages. So depending on whether the GTPC messages are global messages or UE specific messages, you need to determine whether you need to attach a TEAD or not. For example, if you are exchanging S1AP protocol messages between eNode B to MME, if it is a S1 setup request to establish the S1AP relation between eNode B to MME, that S1 setup request won't contain eNode B UEID, eNode B UE S1 APID, and MME UE S1 APID. It won't be present because that S1 setup request is not related to UE specific procedure. It is a non-UE specific procedure, also called as a global procedure. So for exchanging any global procedures, either on the X2 interface or a S1 interface, we won't be using the UEIDs. But at the same time, if you are actually exchanging information related to UE specific messages like creating a ERAB or whenever you are creating a ERAB, you have to tell for which user the ERAB to be created. MME will explain that to the eNode B. So that is very much needed. So there identifying the user ID is very important. Same way in GTPC also we have the general messages available, UE specific messages available. In the UE specific message case, this TAD field will be present and the T flag will be set to 1 in UE specific cases. In non-UE specific cases are global messages that MME to S gateway or S gateway to P gateway, whatever the global messages they exchange. For those messages, T flag will be set to 0 and this field will be absent. This field won't be there in the header. It will be removed. This TAD field will be removed. That's the idea of T flag. And the next 3 bits are going to be spare bits. Um, spare represents no use. Basically, they are used for the future purpose. This spare, just right now there is no purpose related to it. So that is the meaning of spare there. Okay, what is the next field that we have? The next field we have is message type. What kind of a GTPC message we are sending between the components. And the message type size is 8 bits. The possible values we can have is from 0 to 255. So the number of possible messages we can have is 256 different types of messages we can have on the GTPC protocol. So that is message type, which is 8 bits. Um, so 2 power 8 minus 1 is the maximum value possible. So if between all the interfaces together on GTPC protocol, the total number of messages that are possible is only 256. That means between MME to S gateway, S gateway to P gateway, S gateway to SGSN, MME to MME, MME to SGSN, all these interfaces together, MME to MME, all these GTPC interfaces together, the maximum number of messages we can have are only 256, numbering from 0 to 255. Each message is going to be used for a different purpose. For example, for handovers, we will be using different messages. For creating the dedicated bearers, etc., we will be using different messages. So for every different functionality, we will be using a different message. So this message type will be recognizing what kind of message that we are exchanging. That's it. That is this parameter called as message type. And then we have message length. So what is this message length and how many bytes it is? It is 2 octets or 2 bytes. Total length is 16 bits it is. So the minimum possible value is going to be 2 power 0, which is 0, and the maximum possible value is going to be 2 power 16 minus 1, which is 65,535 bytes. So you can have up the message length value that can be represented up to 65,535 bytes. So so this represents the length of the GTPC message, this message length. For example, if the value representing 500, the meaning is including your header and information elements, i.e. is your total message size is 500 bytes. So that is what it represents. For example, um, from the UDP protocol, if we have received 1500 bytes message and the piggybacking flag is set to 0, then typically the message length value will be representing as 1500. That means it is a single message and the message size is 1500 bytes. It is a single message and it is 1500 bytes. Um, that's how it works. And if it is piggybacking flag is set to 1, let us suppose, and if the message length value is the total message size we have received from the UDP protocol is 1500 bytes. The total message size received is 1500 bytes, but your piggybacking is set to 1 and the message length is representing only 500. What is the meaning of it? That means there are multiple messages that are involved here. The first message size is 500 and there is another message attached after first 500 bytes. There is at least one more message present, one more GTPC message present. That is what it represents. So this message length basically represent um, the size of the GTPC message that we have received. So it could be multiple messages or it could be a single message itself. It could be any of it. Okay. And then TEID, tunnel identifier, is going to be 4 bytes. You can read it here that it is from M to M plus 3. That means it is mth byte, M plus 1, M plus 2, M plus 3. So totally it represents 4 bytes of information totally. And the maximum possible value for the TEID is going to be 2 power 32 minus 1. which is around 429 crores. So the number of tunnel IDs that we can create is a really, really big number, up to 429 crores plus, because 2 power 32 minus 1 is that big number. So that represents the number of tunnel IDs we can create between MME to S gateway. We can create 2 power 32 tunnels between MME to S gateway or S gateway to P gateway on GTPC protocol. One tunnel recognizes the signaling messages belongs to one mobile. That's that tunnel ID. Of course, one important point here. The tunnel ID that must be included here is always going to be the tunnel ID created by the opposite guy. What is the meaning of tunnel ID created by the opposite guy? What is the real meaning of that? Let me explain you that concept. If MME is sending any GTPC protocol message to MME is sending any GTPC protocol message to S gateway, MME must include the tunnel ID that is created by S gateway, because it is opposite. It is for receiving. S gateway will be receiving the traffic by using the tunnel ID, and vice versa. If S gateway is sending any signaling messages to MME, S gateway must use the tunnel ID created by MME to send the message to protocol message to MME, so that MME recognizes this message which is sent by the S gateway belongs to which mobile user, which mobile phone, or which UE, which user equipment this message belongs to. You can recognize that. So that's the idea there. So you always have to use the opposite components created tunnel ID as part of your GTPC protocol message. How it works? How you will know the opposite components uh, tunnel ID that is created by the opposite component? We will discuss that concept. We will go into that. But before we go into it, but just a first point of learning is it is always going to be the opposite components tunnel ID, whatever it is created. That's the TAD part. It is 4-byte information. Then we have the next parameter, which is sequence number, which is again going to be another 3 bytes, n to n plus 2. Nth byte, n plus 1 byte, n plus 2 byte. Totally 3 bytes of information. It is going to be sequence number, 24 bits. So the maximum possible value for the sequence number is also going to be a big number, 2 power 24 minus 1, which is like 1 crore 67 lakhs. So you will have that big number. So will be there. So the sequence number is used for identifying the GTPC sequence numbers in the order to recognize any GTPC messages are missing or not. So that is the purpose of the sequence number, because GTPC need to implement the reliability on its own. So GTPC uses the sequence number for its own purpose. For its own, we did not see this kind of a sequence number present in any of the protocols that we have studied earlier, like application protocols. At least X2AP is not having any sequence number. S1AP is not having any sequence number. The reason is X2AP and S1AP will be using SCTP transport. SCTP provides the reliability for application messages. So transport protocols doesn't need to carry this sequence number. Sorry, application protocols doesn't need to carry the sequence numbers. Transport itself will have the sequence numbering on its own in case when we are operating with reliable protocols like SCTP or TCP. But GTPC is working on UDP. As UDP doesn't provide the reliability, GTPC will need to implement the reliability on its own. For that reason, we have this sequence number to detect duplicates or to detect that any GTPC messages that are missing if you receive a message out of order. For example, if you have received a sequence number 165, 166, 167, next you received is 169, you know that there is something happened to 168, the message that is missing. So for that reason, so the sequence number would be used in GTPC messages, both in request time as well as the response time. If you use some sequence number in the request time, same sequence number would be used for the response. Now, if you have used sequence number 167 in the request, if you get a response back with the sequence number 167, you know that you have received the response message for 167th request. You will consider that as successful. If you don't receive the response for the 167th message from the other side, you decide to retransmit that 167th request message once again. So to recognize these kind of things, we will use this sequence number to recognize how many messages you have got the replies for, how many messages you did not got the reply. If you did not get the reply for a particular message, you will retransmit those messages on your own, as UDP is not taking care of that mechanism. So that is the sequence number parameter. And then we have the last parameter, which is a spare. What is the meaning of a spare? Spare represents no use parameter, nothing. It just conveys nothing. It is 1 byte of spare information just got added for future purpose. It is useless. It will be filled with zeros. 1 byte of spare value. Okay. So these are the actual parameters that we have in GTPC protocol so far. Okay. Um, these are the actual parameters that we possess in the header part, not the information elements. This is only header, the common part in every GTPC protocol message. So what is the size of this GTPC header? Um, what is the size of it? So this is 1 byte, this is 1 byte, this is another 1 byte, another 1 byte. Up to here, it is exactly 4 bytes of information that we have. This TEAD part is 4 bytes. If it is present, it is another 4 bytes. And the sequence number is 3 bytes of information, your sequence number. And the spare is 1 byte. So, if you consider the only field that is optional in all these fields is the TEAD part, which may be present, may not be present. Rest of the fields are mandatory in the header. So that tells us that there are only two possibilities. This is total 4 bytes. So 4 plus 4 plus 3 plus 1. Totally it can be 12 bytes if TEAD is present. If TAD is absent, minus 4 bytes, it is going to be 8 bytes. So that means your GTPC header size, possible header sizes are two sizes, either 8 bytes or 12 bytes, depending on whether the TAD is present or not, or depending on your T flag. If T flag is set to 1, then it will be 12 bytes. When T flag is set to 0, it will be 8 bytes, because TAD won't be there when the T flag is set to 0. So, what are the typical GTPC message communication types? What are the different GTPC types of messages we have? So we have two nodes over here, node 1 and node 2. Don't care which nodes are those. Doesn't matter those nodes. It can be any GTPC nodes. It can be one node can be MME, other node can be S gateway or S gateway P gateway or S gateway SGSN, MME SGSN, MME MME, SGSN SGSN. Any two GTPC components. So we are studying the general structure of the messages right now. We are not specifically going through any particular interface. So if node 1 sends a XYZ request in GTPC protocol, immediately what the node 1 does is, after sending the GTPC message called as some XYZ request, it could be any request message, it starts a timer immediately. It will be including a sequence number in the XYZ request, and node 1 will be expecting a response from the other side with the same sequence number in the response message. It will be expecting a response. In how much time the response must arrive? The response must come back before the timer expiry, before the timer expiry. Like The timer can be running for 10 seconds or it could be running for only like 100 milliseconds. It will be dependent on the operator to decide how much time that we have to set between two GTPC nodes. It will be depending on the interface speed and how fast the nodes can process, etc., etc. Operator will determine what will be the perfect timing value suitable for GTPC operations. So, but once the timer is set, node 1 will start the timer immediately after sending this XYZ request message. Before the timer expired, if you receive a response back for the XYZ request message, which is exactly the same sequence number you have used in the request is present in the response, you know that you got the response received. You have to stop the timer and you will consider this procedure as successful because you have sent a request message, you got the response message back. So we don't care what happened at the UDP level. We know that at GTPC level, we know that the procedure is already successful. Now we know that UDP message is also exchanged correctly. How do you know? Because for whatever the proper request you have sent, you have received the response back ultimately. So you know that this operation is successful. It is a very well, perfectly worked out operation for us. Okay, then we have um, other alternative possibilities. What are those? GTPC node 1 is sending a XYZ request message and the timer started, but the XYZ request message did not reach node 2 did not reach because of UDP related problems. The message has missed in the middle. The IP packet has been lost by some router. It did not forward it to the next router because the router has got restarted somewhere in the middle and your IP packet has been lost. That IP packet is containing a UDP inside. Inside that UDP, there is a GTPC packet inside. So we have to consider that GTPC packet is missing. Without requesting a request message, Node 2 will never respond back. So obviously Node 2 will be mum here. It is as if I haven't received any message. In fact, it never received any message. From Node 1's perspective, he has sent a message. It is indeed waiting for the response. It will wait for the response and the timer expired. Um, After the timer expired, Node 1 will come to a conclusion that, hey, I have sent a XYZ request message which I did not got a reply back. So I know that something is screwed up here. So either UDP or IP layer, somebody has screwed up. My message never reached the node B, or I don't know what happened exactly, but I did not receive the reply. What should I do? I have to send the XYZ request once again and start the timer once again. So you repeating it. Now we take that in this scenario, the XYZ request successfully reached, node 2 here. Node 2 also successfully generated the reply, XYZ response. That XYZ response did not reach node 1. It has been blasted in the middle. Again, because of IP problems or your IP packet loss, your GTPC packet has been lost in the middle. Doesn't matter. Now there is no difference between the operation from the first case to the second case. Even in the second case also, your node 1, once it finds out that there is a timer expired without receiving a response, he doesn't care whether node 1 received or not, whether the node 1 generated the reply or not. He doesn't care. From his perspective, reply is not received. So what does he do? He generates the XYZ request message once again, start the timer once again. So his duty is simple. It has to wait for the response for some X amount of time. If not received, you have to keep resending the message until you receive the response from the other side. Node 2 will think, hey, I have already received this request message with the same sequence number once again. One more time I have received it. That means I have already generated the response message and sent to Node 1. Why Node 1 is sending this XYZ request once again? Node 2 will think for some time and say, okay, I think whatever the XYZ response I have generated and sent, I have packed into UDP IP. I think UDP IP might have screwed up somewhere. My XYZ response did not reach Node 1. That is when Node 1 is resending this request message one more time, even though I have received it and sent the reply. So what do I need to do? I have to resend that XYZ response once again. So Now, for example, this time node 2 is sending the XYZ request after the timer expired, after the timer is expired. Let us assume after the timer is already expired, but after that XYZ response is received. So basically, how much time the node 1 will wait is till the timer value is expired. The moment timer is expired, he will start sending the XYZ request once again. Actually, XYZ response is already received by the node 1. But by the time the response is received, he is already triggered the XYZ request. This XYZ request will go to node 2 one more time. Node 2 will think that again my response did not reach node 1 in time, or it may be blasted in the middle. So what do I need to do is I need to generate the response once again and send it. So here node 1 is receiving XYZ response multiple times. Obviously, with the help of the sequence number, node 1 can determine this XYZ response which is received two times is the same response because it is having the same sequence number inside it. So one message I will throw into dustbin, only one message I have to use. But ultimately, the point here is that it could be various situations, like in where you will uh, be retransmitting the request messages again and again until you get your response from the other side. So that's the thing about this. One more scenario. There is another type of messages called as notifications. So what are the notification types of messages? If node 1 sends a notification, XYZ notification, it is just to inform some information to node 2. It is not requesting anything from node 2. It is not requesting any information from node 2. It is telling node 2 that I am notifying something to you. Now, if you send some information to node 2, if node 2 doesn't like it, if node 2 doesn't like that information, for example, node 2 can reply back with um, um, doesn't like it or like it, whatever. But if he receives the information successfully, he is going to respond back with XYZ notification acknowledgement, explaining to the node 1 that I have received your notification. I am not sending any meaningful information inside the acknowledgement. This acknowledgement is only to tell you that I have received your message. I'm not sending anything inside. What is the difference between a response message and an acknowledgement message? Response will actually contain proper protocol details inside it. It contains some meaningful information because by sending XYZ request, node 1 is demanding some information from node 2. Node 2 in fact will include that information in the form of information elements in a response message and send it to node 1. So node 2 requires this response. Inside that, there are some technical details present. But in case of XYZ notification, who is sending the actual technical information is node 1. It is telling the node 2 that if you receive this notification, just send me an acknowledgement. Inside the acknowledgement, there won't be any technical information, any technical details that are present. It is just a acknowledgement. It is just to explain the node 1 that I have received your XYZ notification message. For example, if node 2 doesn't send the acknowledgement, what does node 1 do? Same concept. He will wait till the timer expiry. Within the timer expiry, if it is not receiving the acknowledgement from the other side, automatically node 1 will transmit the notification once again. So it will keep transmitting the notification until and unless you receive the acknowledgement back. But only the difference between request and response and notification and acknowledgement is in request and response, both request and response messages are important. Both are containing some proper protocol information inside. But in case of a notification and acknowledgement, only notification contains some protocol information which is getting conveyed from node 1 to node 2. Acknowledgement is just an GTPc level, you know, uh, reliability mechanism to make sure that the message is actually reached at the destination. To you are just waiting for that acknowledgement from the other side to get that guarantee that it is received. That's it. It is not containing any technical details, much of the technical details inside. So that's acknowledgement. So these are the different types of GTPC messages that we will have. Next set of GTPC messages. Node 1 will send something called as a command. There is another type of procedure called as command. It sends XYZ command. That means node 1 is commanding node 2 to do something or to initiate a procedure. It'll be demanding node 2 to initiate a procedure by sending this command. What does node 2 do? Node 2 will initiate a request message. So it starts a timer. Within the timer expiry, node 1 is expecting a procedure to be initiated by the node 2. Typically, GTPC procedures are initiated with request message. So we are we are triggering node 2 to generate this request message by sending this command, and node 2 is sending the XYZ request. And of course, node 2, whenever it is sending a request, it need to start a timer. Within the timer expiry, we have received this XYZ request. Node 1 will think that it is justified because it has sent XYZ command to command the node 2 to start a procedure. It indeed started the procedure within the timer expiry. We consider that that is successful and we stop the timer. We stop the timer that is running. But now node 2 started the timer after sending the XYZ request to node 1. Now node 2 is waiting for XYZ response from node 1. Within the timer expiry on the node 2 side, node 1 must send back the response. So if it sends back the response within the timer expiry, so it stops the timer and it considers that the procedure is successful. So totally here, the procedure is containing three steps. So we can have two types of proper GTPC procedures. Two-step procedures, three-step procedures. In two-step, it is just request and response. In three-step, command, request, and response. This command will trigger the procedure. Okay. Now, when you send a command, there could be other alternative that can happen. If one node sends the command, if the other node don't like it, for example, if the other node won't like it, the command that we have sent, instead of triggering the XYZ request, the node 2 can respond back with XYZ command failure. Hey, sorry man, you have sent me a command to ask me to trigger a procedure, but I'm not accepting it because of so and so reason. I'm reporting a failure. So either you need to start the procedure by sending a request, or you have to report a failure, explaining that no, I won't start the procedure that you are asking me to start. Sorry, I won't do it. It will node 2 will bluntly tell this to node 1. But of course, whatever the decision it may take, node 2, either to trigger the procedure requested by node 1 or to reject it, but that has to happen before the timer expiry. So node 1 started the timer. Before the timer gets expired, we must respond back with something. If you don't respond back with one of the two things, either XYZ request or XYZ command failure, node 1 will think that the XYZ command message did not reach node 2 and it will retransmit it automatically, because GTPC need to take care of its own reliability as it is using UDP transport. UDP doesn't provide reliability. It is implementing the timer based reliability. So it is starting the timer for every procedure. Within the timer expiry, you are expecting some sort of a response from the other node. If you don't receive it, you automatically assume that your command or your request message is missing. You will retransmit that. That is how the GTPC implements reliability mechanism, self-implemented reliability. So, but if you receive a failure, you stop the timer. So typically these are the GTPC messages that you can find between GTPC nodes. These many types will be there. What is this XYZ? That XYZ can be anything, different protocol messages. I just have called it as XYZ. I could have called it as ABC also. Simply the meaning is some command, some GTPC message. That is the meaning of it. But the last word will be either command or request or notification or whatever. Only those words will be used in the last word. So what type of GTPC protocol message types we have, and which messages can be used on what interfaces? So these tables will show us that. These tables will tell us that. So we have the first table numbering from 0 to 94 here. Actual command codes we can have from is 0 to 255. The maximum message codes we can have on all the interfaces together. And here in this table, we have listed 0 to 94. 0 reserved for future, no use. Command code 0. Message type 0. Message type 1, 2 are used for something called as echo request, echo response. 3 is used to report version is not supported, called as version not supported indication. 4 to 24 and 25 to 31 are reserved for two special interfaces called as S101 and SV interface for SRVCC operations. Uh, so those are used for some other protocol interfaces, not the traditional interfaces. These are the new interfaces that are getting introduced in GTPC. And what protocol messages we have from starting from 4 to 24 and 25 to 31, that protocol information will be available in these documents that are listed on the right hand side. 29.276 document and 29.280 document. In those documents, we will have those command codes. So that means GTPC scope has been expanded, and other than the interfaces we have identified, some of the latest advanced LTE concepts also we will be having GTPC used on these two interfaces as well, S101 and SV interface as well. So when you are using it GTPC on those interfaces, some protocol messages required to be reserved for that, and those things are derived in these particular specification documents. Uh, and Codes 32 to 37 are used from either SGSN to P gateway or MME to P gateway on these interfaces. SGSN to P gateway, meaning SGSN to S gateway, S gateway to P gateway. On two interfaces, we'll be using this particular messages. MME to S gateway to P gateway. It is a combined procedure. MME initiates it, it goes to S gateway forwards that message to P gateway. P gateway replies back to S gateway replies back to MME. So basically, we are achieving the coordination between three components. MME, S gateway, P gateway are getting coordinated with these procedures. So our SGSN, S gateway, P gateway are getting coordinated. SGSN will trigger this procedure in case if the mobile is present in UMTS network and using the LTE core services. The procedure would be triggered by SGSN. It comes from SGSN to S gateway, then from S gateway to P gateway. The procedure move further from S gateway to P gateway. So that's the idea. Okay, so these are used on S4 and S5S8. S4 means SGSN to S gateway, and S5S8 is S gateway to P gateway. Or S11 plus S5S8. S11 is between MME to S gateway, and S5S8 is between S gateway to P gateway. So create session request message is originated by MME. MME sends it to S gateway. S gateway do some stuff and forward that message to P gateway. P gateway receives the create session request, do some stuff, and generate a reply called as create session response, and send that create session response back to S gateway. S gateway do some more stuff and send that create session response back to MME. So totally, this particular two messages are exchanging the coordinate, are achieving the coordination between three components, which is a rare protocol phenomena. Till now, whatever the protocols we have studied are all between two components always. For example, RRC is the protocol existing between UE to eNode B. No other component will be involved. NAS is the protocol between UE to MME. No other component is involved. S1 AP is between eNode B to MME. No other component is involved. eNode B to eNode B, X2 AP protocol only between eNode B. No other component is involved. But here, GTPC protocol is achieving coordination among multiple nodes. So it's exactly the same way how we have create session request. We have modify bearer request and modify bearer response, delete session request and delete session response. Now you can observe the notations here, request and response. So that is the typical convention we use in GTPC. If you send a request, you must receive the response back within the timer expiry. Otherwise, you retransmit that request once again. And then um, 38 and 39, the protocol message types 38 and 39 are used only between SGSN to P gateway, not applicable from MME to P gateway. Only for 3G operations, we'll use these two protocol messages, change notification request and change notification response. And some more messages are reserved for the future. 40 to 63 are for future use. That means there is no purpose identified for these numbers. Starting from 40 to 63, they have kept it for future need. Right now, there is no, those numbers are not used. 64 to 73, different protocol messages would be used on different interfaces. If interfaces are not specified, the meaning is um, those messages can be used on any interface. If interface name is not specified anywhere, those messages can be used on any interface. For example, if you see the below things, trace session activation, trace session deactivation, stop paging indication, all these things can be used on any interface because the interface is not mentioned specifically on what interface it should be used. But for the commands starting from 64 to 70, for every protocol message that is there, those are majorly commands and failure indications. Command failure indication, command failure indication, notification failure indication. For those things, you have interfaces identified. So, for example, modify bearer command is triggered from MME to P gateway, meaning is MME to S gateway, S gateway to P gateway, or SGSN to S gateway, S gateway to P gateway. So we are using it on those interfaces. So modify bearer command. If that is being rejected, you will be getting a failure indication from the other side. If that is getting rejected for any reason. So that is that. So um, without studying the technicalities of it, there is no point in understanding this thing. But I hope you already got the concept here. There are a lot of messages on these protocol interfaces. We need to study all these protocol messages and what for what purpose we use them. Now, here the protocol messages that are listed from 95 to 100 are in reverse direction. P gateway initiates these procedures, request messages towards MME. P gateway to S gateway, S gateway to MME. Request will arrive and MME will respond back with response. MME to S gateway to P gateway, the response will be sent. Again, the coordination is achieved between three components here also. Same way, update bearer request, delete bearer response. So all these things are for different purposes. Similarly, we have 128 to 141, the below list: MME to MME, SGSN to MME, MME to SGSN, SGSN to SGSN. Mostly these MME to MME, SGSN to MME, MME to SGSN, SGSN to SGSN will happen for the purpose of handovers, to move the mobile equipment from one technology network to another, one node to another node. We will be using these interfaces. So most of these messages listed in this category, S3, S10, and S16 interfaces, are going to be useful for handover related procedures, all these protocol messages. So a lot of numbers are again reserved for the future use, and some more messages, SGSN to MME, MME to SGSN, only on S3 interface. Some messages are there only on S4 or S11 interface, either between MME to S gateway or SGSN to S gateway. P gateway is not involved with these steps, with these messages. Only these messages are exchanged between MME to S gateway. That's all. S gateway will reply back without consulting P gateway. Here the coordination is not there. It is direct communication between MME to S gateway. So if MME sends a request, S gateway immediately send a response back. It won't consult P gateway. So like that, we have some more messages from S4, S11, and some more messages on S4, S11, and a lot of numbers are reserved for the future. And if you continue further, so we have 200 to 255, uh, S gateway to P gateway, P gateway to S gateway, and some more numbers reserved for future. 231 to 236 used for MBMS operations, again on an interface called as SM and SN interface, which we haven't yet introduced. So on that interface, we'll be using these MBMS related GTPC protocol messages. So, and the rest of the things are up to 255 are reserved for the future. So there are a lot of numbers which are reserved for the future on your GTPC information, GTPC protocols. Lot of messages. So um, we did not introduce none of the messages, and what is the purpose of those messages. That is the total thing that we have to study about GTPC protocol. The total thing we need to study. So we will be started to learn these messages one by one. We will try to complete the messages which are easy messages in today. For example, we have echo request and echo response messages. What is the purpose of these messages? Echo request, echo response. These are called as path management messages. Echo request, echo response. For example, suddenly if a GTPC node detects that the other node is not sending any GTPC messages to it, if you recognize that the other node is idle for some long time, you will get a doubt that is the other node actually dead, or is something happened to him? Why he is not sending GTPC messages to me? Is it because genuinely he doesn't have anything to share with me at this time? Or is it because the other node is dead? I wanted to find out. So in such kind of, whenever you get the doubt that the other node may be down, you will be automatically triggering this echo request procedure. So this echo request and echo response is to validate like the other component is dead or alive. So whenever the path become inactive, the components will initiate this echo request procedure. The other component, if he is not dead, he comes back with a echo response and tells him that, hey man, I am not dead. Don't think that I am dead. Genuinely, there is nothing going on. All the mobile phones, I think, are sleeping. It is night 3 o'clock. Nobody is operating. That is why there is no traffic going on between you and me. And that's that. So nothing to send. So as soon as node 1 detects that there is some inactivity, there is nothing going on, it starts a timer. He wanted to see how much time there won't be any traffic. After the timer expired, after he detected that like 5 minutes there is no message, So I have waited for enough time. There is no message arrived from the other side. Node 1 will think that I am working. I am not sending messages to Node 2 because I don't have nothing to share. That's why I am not sending any messages. But is it the same scenario from Node 2 or is Node 2 dead? I want to find out. So what do? I send a echo request message Node 2 asking him, hey, what happened to you, man? Is it the same thing like me or is different situation for you? If you are live, come back to me. In this echo request message, node 1 will include something called as a reset counter. This reset counter informs node 2 about how many times node 1 has restarted so far. Every time this reset counter value will be incrementing. For example, present value is 15. If node 1 goes for a reset, like restarts one time, one more time, the value will become 16. So if the previous value was 15, now the value you have sent is 16, the node will understand that between the previous time and this time, the node has got restarted. So there is a restart happened. So to recognize a GTPC component has been restarted or not, we use this reset counter for recognizing that. So that reset counter related information will be included in echo request. Node 1 informing to node 2 that hey, I'm sending this message as I have got a doubt that you might have been dead, and I am reporting my reset counter value, and please come back to me with your response. So if the response comes back from the other side, you say that the node is not dead, he is alive. In this response message, node 2 may include his reset counter, how many times he has restarted. The value may not be equal. The value will be dependent on how many times node 2 has restarted so far. Value could be a different value. So that is echo request and echo response. These are general messages. These are not related to any UE specific functionality. These are general information that the components are exchanging. Nothing specific to any mobile. Same way, if node 1 sends any XYZ message to node 2, if node 2 cannot understand that protocol message because it doesn't support the version that the node 1 is sending. For example, if node 2 is a UMTS node, node 1 is a LTE node. LTE node is sending GTPC version 2 protocol messages. Let us suppose your SGSN doesn't support version 2. It is only working with version 1. It is not having the version 2 software. So what does node 2 do? Node 2 will come back and explain Node 1 that I'm sorry, man, I cannot understand GTP version 2 protocol messages. I'm sorry to tell you, you have to talk to me by using version 1. So Node 1 itself have to backtrack. You need to go to the GTP version 1 protocol mechanism and communicate with SGSN instead of using version 2. So you have to go to the older version and talk to the old node, because old node cannot upgrade itself to the new version. You have to go back because yeah, your LTE nodes must be supporting version 2 as well as version 1 both. But your UMTS nodes may be supporting version 2, may not be, but they definitely will have version 1. But they have version 2 or not, that will be dependent on whether the SGSN is upgraded with the latest GTPC software or not. If it is already upgraded with the latest software, it will contain that version 2. It will not send this version not supported indication. Otherwise, if you send any message to him, it will tell you that version not supported. Then you have to stop sending version 2 protocol messages, and you have to start using version 1 protocol messages, which could be understandable for Node 2. Again, this version not supported indication message also is not a UE specific message. It is a generic message just to explain node 1 that what versions I support. He explaining that I don't support version 2. That's it. That is the purpose of this version not supported indication. So what information elements we will have inside this? Version not supported won't contain any information elements. It will be zero information elements inside version not supported. But in case of echo request and echo response, in case of a echo request, there can be two information elements. One is a recovery parameter, nothing but a restart counter, how many times your node is restarted so far, which is a mandatory IE. Along with the header, you must have this information element present. But the second information element we may have, which is optional information element called as private extension, which carries some general information. It is not technical information. It can be operator specific details also. So operator may include some private information that he wants to send to the other node. So this is nothing related to any protocol information. It is just private information, as the name itself suggests, private extension. Um, that kind of a possibility is there on the GTPC interfaces to send some private details with GTPC protocol by including it. It is some text information, textual information, this private extension, but it is not mandatory. Most of the cases, this IE will be there in every GTPC message, but in most of the GTPC messages, it will be ignored. It will be considered as optional. So you never send it. Mostly you will be sending only the mandatory parameters. Now, if the other node is replying back with the echo response, these are the information elements that may be present in the echo response. Recovery information element is mandatory, and there is a cause parameter. If there is any problem that occurred on the guy who is responding back, if he is telling that he has restarted recently, it will explain for what reason it has restarted. For example, if the recovery value has been incremented from the previous value, it will explain the reason for the recovery value increment. That means why the node has been restarted, like a hardware failure, or because of what reason the node has been restarted. If there is no restart happened and the recovery value not incremented, only recovery value will be present. Previously received value is 155, now received the value is 155. It not changed. That time your cause won't be included. Cause IE will not be present. If cause IE is present, the other guy is explaining you about some trouble it has encountered. It has experienced a trouble. It is explaining you about the trouble. If the cause IE is included, if the cause IE is not included, the other guy is telling everything is good, man. Our path is working properly. You have sent me echo request with your recovery value. I'm sending echo response with my recovery value. Everything is going good. I think genuinely there are no mobile phones operating right now at night 3 o'clock. So that's why there are no messages going on between you and me. Don't worry. Path is working properly. So these are called as path management messages, managing whether the path is working perfectly or not. That is the meaning of path management. Again, the third IE that could be present is private extension. Again, optional, may be there, may not be there. O stands for optional, M stands for mandatory. So only echo request and echo response will contain the information elements, and version not supported won't contain any information elements. It will only contain a message code. It will only contain. What is the meaning of message code? For echo request, the message code is one in the header. Um, for echo response, the message code is 2. For version not supported, message code is 3. So only header, in the header, message code will be containing a value 3. That's it. In the header. We already know the header, we studied the header. So this message type value here will be set to 1 in case of echo request. The value will be set to 2 in case of echo response. It will be set to a value 3 in case of version not supported. When the value is 3, your message will be finished with just header itself. You won't have any IEs present. Information elements are 0 in case of version not supported, because that's what we have learned. Every GTPC message standard contain header. IEs can may be present, may not be present. 0 or more information elements. So in case of echo request, echo response, we have IEs. In version not supported, we don't have any IEs. So nothing to study there. Only the header thing. And that too, in the header, T flag will be set to 0 for all these three messages, and TEID field will be absent. It won't be present because these are not UE specific messages. These are generic messages. All the three messages are general messages. So T flag will be set to 0. TEID will not be present. So header size only will be 8 bytes for these three messages. So that is the first set of messages we have completed. We will continue with the further messages in our next session.